Stibitz, and the title is K-stability and Sarkisov.
All right, so what I'm going to be talking about today, well, we're going to have X is going to be Q factorial Fano variety. And I'm going to make a couple more assumptions. First, that it's the Picard group is isomorphic to Z, and that it has terminal singularities. You might be able to get away. You have to interpret some of the things differently if you don't assume this, but there's some versions of statements that hold if you just have KLT singularities. Okay, so this is obviously a setup we can ask about K-stability, and this is also a Mori fiber space, so it makes sense to talk about Sarkisov links. So at least these two words make sense for what I'm talking about. And then the basic question I want to ask is, when is X K-stable, or when can I compute this in practice? So not in theory, but in practice. And so let's go back to some of the things we've seen so far in this conference. So the first things we have are the alpha criterion, which go back to Tion. I guess I'm going to worry both about K stability and K, when things are not K stable or not K semi-stable even. So what do we have? I'm not going to write all the boundary cases, but if alpha of x is greater than n over m plus 1, then x is K stable. So this is due to, inspired by Tion, he was asking about Kähler-Einstein metrics, but in this form, Odaka and Sano. And in the other direction, if we want to prove something is not K-stable, we can still use the alpha invariant. And what do we get? If the alpha of x is less than 1 over m plus 1, then x is not K-stable. Okay, so the alpha of x is the first real way we can actually try to compute them. It's pretty easy to compute. People have seen alpha. I don't need to write does anyone want a definition? Okay, I think we've seen this enough where I'm not going to write down a definition. But this is really the first way we had to get our hands on these, apart from maybe explicitly constructing a metric from the complex point of view. Okay, and then this is obviously, there's a big gap between these two numbers. And recently, to bridge this gap, there's the beta invariant of Fujita. And what is it? So I should give a definition this time, though we've already seen this at least once or twice, this definition. Well, what is it? We're going to take, for any divisor e over x, we're going to take this number here, which we take the log discrepancy, times the anti-canonical volume, and subtract off this integral here, which is the integral of this volume where you pull back to some resolution and then ask how much does this vanish along. And you integrate this out to infinity. Obviously, you don't need to integrate it out to infinity because at some point this volume will become 0 at the pseudo-effective threshold, which I'll talk about later. Okay, so this, and then I should say maybe pi is some log resolution. Okay, so what do we know about this? So this, as opposed to the alpha invariant, gives a criterion, a necessary and sufficient condition for K semi-stability, K-stability and K unstability. You can do semi-stability as well. I'm not going to write it down because other people have talked about this, and I'm really you can fill in the details if you want. Okay, so what is the theorem? So we have, I'm going to put a bunch of names here instead of, so we have Fujita, Lee, and Bloom, and which should probably have Bloom and Shu because I'm gonna use these. I don't necessarily know that all these are going to be dreamy, so I'm going to have to use Bloom and Shu as well. If I'm forgetting anyone, please let me know. Okay. Okay, but what does it say? It says that if this beta invariant is greater than 0 for all E, then this is equivalent to being K-stable. And if this is less than 0, obviously you can treat the case where some of them are 0 and here is for there exists a E, then this is the same as being K unstable, which I mean X is not K semi-stable. Okay. So this gives, we can actually give a characterization of being not K semi-stable or being K stable. On the other hand, this is much harder to compute than the alpha invariant. So my goal today is to give some criterion in between these two. It will be based on this beta invariant, but coming from the geometry of X. So remember, X is, in my case, is Picard number 1, which is going to be important for what's to follow. But otherwise, and it's terminal, I guess. Okay. So now I've talked about we've already seen all this for K-stability. Let me talk a little bit about Sarkisov links. We haven't seen as much of that except this morning in the conference, but let me just review the basic idea of Sarkisov links. Maybe I can use this board. Yeah. What do we need? So it's probably enough to just take exceptional.
So if it's only exception, but if it's not exception, what is AEX?
The discrepancy? Yeah. Yeah. I mean, this isn't.
For this, we need
Okay, all my divisors I'm going to be taking are going to be exceptional in practice. Okay, so let's talk about Sarkisov links. And what is the basic idea is we're going to have a Mori fiber space. Recall that X, because it's Picard number 1, is going to be a Mori fiber space of our point. But more generally, we're going to have a birational map between two Mori fiber spaces. So this is birational between Mori fiber spaces. And the idea of the Sarkisov program or Sarkisov links is to factorize this birational map into smaller pieces. So what are the smaller pieces? Write them down now, for those of you who haven't seen them before. So maybe say what I just said in words. So the Sarkisov program is then factorize the birational map F between these Mori fiber spaces into chain of links, and the links are as follows. So we're going to have 4 types. And okay, what do they look like? Well, there's going to be type 1. Here we start out with our Mori fiber space X to S. We're going to have a divisorial contraction over it. We're going to have this sequence. It's going to be a bunch of flops going to some X prime. And this is going to have a Mori fiber space structure on it. So S prime, and you're going to get a map like this. type 1. And you should you can think about these for either surfaces or threefolds if you want examples. There's type 2. In this case, we take X, which has a more fiber space structure like this, and we're gonna blow it up. Take our map like this, which is the only thing I'm going to need about this map, I think. I mean, I'm going to construct these in some examples, but the only thing I'm going to need is that it's small, for what I'm going to say. It follows, so nothing's contracted either way. Okay, so we have it going to like this, and this is going to contract a divisorial contraction to another Mori fiber space, X to S prime, and these have to be equal. And these are types 1 and 2. There's 2 more types, which I'm going to put on this board. So what else can we have? We can have the opposite of type 1. This is called the type 3 Sarkisov link. X to S. Here we have S prime over X prime and Y prime. This is a contraction. Anytime I write Y to X, that's supposed to be a divisorial contraction. The X to S are all Mori fiber spaces. I guess I'm not going to, you can say more about what S prime to S and S to S prime are as well, but I'm not going to worry about that, especially because in my case, one of the S's is a point always. And then our last type of Sarkisov link looks like this. X to S, and then you have another T over here, S prime, and our map already on X. Okay. So these are the Sarkisov links, and the idea is to factor any birational map between Mori fiber spaces into a composition of this. And this is an idea that goes back to Sarkisov, who did this for conic bundles. And the full program was proved for threefolds by Corti and then there's a couple different things. I think there's a couple. Yeah, I don't need to worry about. Yeah. Yeah. So you can break it up further in that case onto what that map is, but I don't want to get into that. Okay. I won't actually need the full Sarkisov program. Maybe I should say what's been proven about it, though. But so this goes back to Sarkisov. So he developed the ideas. I'm going to say Sarkisov's program because it's named after him from the 80s. Corti in the 90s proved it for threefolds using MMP for threefolds. And then in higher dimensions, Haken and McKernan used the results to show factorization. I think this was 09. Okay. I won't actually need the factorization. All I'm going to be worried about is the first Sarkisov link out of our variety X. But you should think that any birational map we're getting is going to factor like this. So you're going to get a first one in particular, and that's what I'm interested in. Okay, and so how do these topics relate? Maybe I should talk first about birational superrigidity and rigidity, which has been mentioned multiple times so far. But it's a starting point for where I approach this problem. So let's just recall the definitions. So I'm just going to be give the definition for a Fano variety. So we'll have x as before, where it's going to be, the base is going to be a point now. Obviously here I allowed more, but now we're going to go back to, I think for the rest of the talk, that x is always going to be over a point. So what do we have? So this has been given. Then if we have a birational map x to a Mori fiber space y to s, any birational map, so this should be a Mori fiber space, and this is, and it satisfies that x or y is isomorphic to x, and this is going to be called birationally rigid. And if this map f here is an isomorphism, it's going to be super rigid. And this is super rigid. Okay. So birationally rigid varieties are going to have some Sarkisov links, but all these Sarkisov links are going to be to itself. I mean, you can see what type they're going to be, because we don't have any birational maps to higher dimensional things. You know, we can only have this type. Is that right? Yeah, that's the right type. And then super rigid things should have no Sarkisov links. So this is how those relate. But we could consider other things as well, but I want to go back to a theorem that I proved with Sichuan, relating this to K-stability. And this is the theorem says that if x is birationally super rigid, and this condition on the alpha invariant, so we want to prove something's k-stable, and then for that we would need the alpha invariant to be bigger than n over n plus 1. Here we only need it to be bigger than or equal to 1/2. And then our conclusion is x is k-stable. Okay, and what's the idea here? In a couple words. The idea is to combine Fujita's beta invariant with the Noether-Fano inequalities. So we're going to make an estimate of beta invariance using the Noether-Fano inequalities. Okay, so maybe I should say what the Noether-Fano inequalities are. We saw them this morning, just for people who don't usually think about these. The Noether-Fano inequality is going to say that if we have something that's super rigid, or super rigidity is equivalent to not having a movable linear systems that are too singular. And what do I mean by too singular? Well, the amount of singularity is going to be measured by the canonical threshold. So what is it going to say? So one direction of this goes back to Iskovsky. But the other direction is due to Chelsov and Shromov. And then what it's going to say is that x is birationally super rigid if and only if for every movable pair x m, where m is going to be q linearly equivalent to minus k of x, then this is canonical. Okay, so this is quite similar to alpha invariant. The difference is we're taking movable, I should say this is movable, and we're using the canonical threshold versus the log canonical threshold, but otherwise it looks the same, and that's part of the idea of this proof here when I'm talking about estimating the beta invariant. You do the same kind of thing where you'd estimate the beta invariant using the alpha invariant. Okay. So this works for birationally super rigid things, but as we've seen throughout this conference, there's many things that have some other Mori fiber space structures and hence are not birationally super rigid, but we can still hope to say something about them. And that's what I'm going to talk about. Is what do we do if a terminal Fano variety is not birationally super rigid? Maybe it has a few Sarkisov links that we can explicitly compute, and then can we say anything about the K-stability? Okay, so let's go back. So I want to say something. If I can describe the Sarkisov links, then I can say something about the K-stability. So how do these two even relate? I mean, here it came from the northern Fano inequalities. Let's think even further back. How do these Sarkisov links relate to K-stability? And the one thing you can think of is that if we have Sarkisov links like this, y going down to x, remember x is always over a point. If we have this type of type 2 Sarkisov link, I don't know why I'm doing the type 2 first, or a type 1 Sarkisov link, this comes with a divisor e, or if we have e goes to y like this, this is fine, where this is a Mori fiber space. Then we get a evaluation or a divisor over x coming from this process. So the next real question is, what is beta of e, or if you like, using the delta invariant, I guess delta of e, I don't know, even know if this is the right notation, but whatever this would be, where you take the log canonical threshold over this integrated volume. What's the correct notation?
A over S.
Yeah, I didn't want to write a. Okay. A of e over. Okay. S of e. Okay, so we want to say something about these in terms of some data. The Sarkisov links like this. So the first thing we need is, I guess, what data we would need. And we're only going to estimate these. So our goal now is to estimate, both from above and below this beta v in terms of data from coming from the Sarkisov link that is explicitly computable. So our goal now is, and in both of these, the key thing is this integrated volume S to B, which was the integral over there, maybe up to this factor of whether you divide by the volume or not. I think I did not divide by, that was up to a multiple. It's that integral. Okay, so our goal is to find upper and lower bounds for this integral S sub E, which here I'm going to divide by the volume, which is this integrated volume. And what do I want these bounds to be in terms of? So you could, if you knew enough about this, you could obviously compute them explicitly, but I don't want to have too much information going into these bounds. So in terms of a few invariants from the link, I'll actually just need 6 numbers, and I can even get bounds with just 4 numbers that are useful. Okay, and so the estimates come, there's 2 parts to them. One is a general thing, fact that works for any divisor. It's very general. And the other will be data identifying what we get for a general divisor in terms of the invariance of the link. So I'm going to break it up into 2 parts. All right, the first part is the general estimate. And what is this going to be in terms of? So some forms of these came up in my work with Zitwan and his subsequent work. But what are we going to have? We're going to have the tau v, which is the pseudo-effective threshold. So when there stops being sections, we're going to have eta v, the order at which our sections stop moving, which is called the movable threshold. And then in terms of the volumes, and you can get rid of these last two numbers if you want by further estimating. So we're going to have minus kx to the n. Actually, I'm going to give this another name so I don't have to keep writing this. Write this v for the volume function because I don't want to keep writing that. So it looks like v0 for minus kx to the n, and v eta, the volume at the movable threshold. Okay, so volume of minus pi star kx minus eta e. Okay, and if you want, you can get rid of the volume things by further estimating the volume. And this is actually what's happening in the work for superrigidity. You don't even need this. And I think for my applications, you don't need it either. Okay, so that's part one. It's a general estimate. It actually holds for any divisor. There's nothing about the Sarkisov link coming in. And then two, we're going to have some identifying all these numbers. So tau, eta, and these v0 and v eta in terms of some numbers coming from that I use to say something about the Sarkisov links. So geometry of link. And I guess I think I forgot to say that these are the only two types of links that start with a Fano variety of Picard number 1. The other ones are only for Mori fiber spaces over higher dimensional bases. So these are the starting points. And the starting point is usually if you're trying to compute something, as we saw this morning, these are where you start from. Okay. So let's say let me talk a little bit about the estimates now. So what can I say about those? Let's go back to part 1. So now we want to estimate this integral that we've seen a few times throughout the conference in terms of those invariants there. The idea is pretty clear. So for the general estimate, what are we going to use? Well, we're going to use log concavity of the volume function to get lower bounds. We'll use log concavity of the restricted volume to get upper bounds. And by restricted volume, I mean the volume when you restrict to E. And then, so this doesn't say how the movable threshold's coming in, but after the movable threshold, so if we're looking at this as a function of t, after the movable threshold, this volume function is very explicit. So we know the volume function, v of t after the movable threshold data. Okay, and this is what goes in. And I'm just going to tell you what comes out of it. It's just integrating and integrating twice in the case when you use it. Restricted volume because that's a derivative. So what do we get out of it? We're going to get a lower and upper bound for this integral s to d. And I'll write them on the board. So the lower bound is actually not the prettiest. So it's going to be something like this, eta over n plus 1. And then we're going to have 1 plus volume of eta. There's going to be the ratio of these volumes raised to the 1 over n, and then we add the same thing raised to the 2 over n. And then this term, you keep adding until you get up to the last term, and you're going to have to modify the last term because there's going to be some part of the volume coming from after the movable threshold, and this is going to give you tau over eta, which is bigger than 1, v eta over v0.
Why do we know volume after?
Okay, so if you're after the movable threshold, your Picard number 1, you have to be divisible by enough times of the most singular divisor on your thing. The thing computing. Yeah. So this is what the key fact used in the super rigidity thing. Yeah. So Picard number 1 is already used here. Okay, and then so this is just coming from log concavity of the volume plus this, and then the other direction we use the restrictive volume, and it's going to give something like this. So S sub E is going to be less than or equal to, let's see if I can write this down, eta plus 1 over n plus 1 tau times tau minus 2 eta over tau minus eta, and then we have the ratio of the volumes again. So at least we don't have as many terms, but maybe this number's a bit more ugly. And if you want to, you can further estimate the volume at the movable threshold in terms of the volume, also using the log concavity, and so you can further estimate again, and this will give you something that already occurred in Sichuan's work. So this is even another estimate coming right here without any volumes involved. You can probably get a similar thing here, but in general, you don't want to do that if you already know the volume because you want the best estimate possible. But in this case, you want the most general estimate possible, so this is useful. Okay. So this is how these are general estimates. There's nothing about the Sarkisov link occurring here. So now let's talk about the Sarkisov link and how that has to do with anything I'm saying. Here? This is 2 over n. And you just keep doing the powers, except for the very last term, you have tau over eta as well. It's not the nicest expression. Maybe it's not the nicest form to put it in. But it's computable, very computable from 4 numbers. So. Okay. So now let's go back to the Sarkisov link. So you should think we're going to have some Sarkisov link starting from our Fano variety, and what do we actually need to know to compute these numbers, and that's what I want to know. So let's write something about the setup first. So step 2, and I'm only going to do this for the type 2 Sarkisov links now. I think this is more interesting. You can certainly do it for the type 1 case as well, and the type 3 and 4 don't occur for starting with a Fano variety. Okay, so what are we going to have? I'm going to need to name a bunch of things. So we're going to have our E on Y. I'm just drawing my Sarkisov link right now. X, let's call this map pi. And we have our map F. Okay, yeah, that should be fine. Y prime. This contains another divisor E prime, mapping down to pi by pi prime to another Fano variety of Picard number 1. And we've seen many examples of these kind of Sarkisov links. When you have a birational involution, these show up. Yes, so I can still get some of the formulas I write down will still work for non-terminal things. Some weird things happen. The Noether-Fano. So the Noether-Fano inequalities in this case will turn to an inequality, and then something a little weird happens when this is KLT. So I haven't, it should be useful in that case as well, but I haven't been able to really apply it. Okay, so I maybe should write down all the numbers, and then I'm going to need a couple more things. So I'm going to need the strict transform. You push E over into here, and you're going to get what I'll call E bar, and same thing for E prime. So E prime bar. And
What do you mean by step 2?
Step 1 was a general estimate. All I'm doing, there's no Sarkisov link involved. You have the movable threshold, the pseudo-effective threshold, and the 2 volumes.
So E prime are essential divisor of I used.
Yeah. Yeah, I haven't written all this down. I don't know how much I want to write down because my handwriting takes up a lot of space, but okay. So what do I have? I'm going to have x and x prime are terminal Picard number 1. You can get away with some KLT singularities. What I'm going to write down is the same. The Sarkisov program. It's going to look a bit different, but it should still, what I'm going to write down will still work. Y and y prime also the terminal Picard number 2. What do we have? This should be small. I don't actually need to know how it's decomposed as any more than that. I just need it small for what I'm going to say. If you do know how it's decomposed, I think for threefolds you might be able to say something more, but in general, it's hard to use any information about that. At least I don't know how. These are divisorial contractions, and those are the exceptional divisors. Okay. All right. So what do I want to? What numbers do I want? I have input data into this, and this is what you should compute. Or I mean, these aren't very hard things, but here's my input data, which I want to know about. So these come from the geometry. You should have the discrepancies. So I'm going to write A for the discrepancy, not the log discrepancy. Discrepancies, the same reason the canonical threshold appears in another final inequalities. Discrepancies are the more natural things here. So this is A E of x. And the same thing for the other side. A E prime of x prime. So these are discrepancies. And then I'm going to need E, which is maybe a bit weird. So this is going to be the number. So we're going to look at E bar. This is why I need to introduce notation for it. We're going to look at what multiple of the canonical divisor on the other side is this Q linearly equivalent to. So this is going to be just keeping track of where this ends up when you push it forward like that. And same thing, you do the opposite thing for E prime. So E prime bar is going to be Q linearly equivalent to minus E prime KX. And then I also need the volumes of the two. Minus KX to the n and minus KX prime to the n. Okay, so this is all the data I'm going to use to compute these bounds. And so now I should tell you what we actually get. Let's see. So, and as you see from here, what do I need? I need the pseudo-effective threshold. I need the movable threshold. And I need the volume at the movable threshold. Obviously, I gave V0 as one of my input data. So I'm not going to say anything more about that. So, but what are the output from doing these computations? So the pseudo-effective threshold is very simple. In this case, it's just A plus 1 over E. The movable threshold is also very simple, but a little more complicated. A plus 1 over E is 1 minus 1 over 1 plus A prime E prime. And if you don't like this, so 1 plus A prime E prime, I call this R prime. This is exactly, so if you take H prime on this side, something very ample, Q linearly equivalent to minus KX prime, and push it forward over here, then this is the multiple it's going to end up in. So this is something, this number here is something you actually probably would compute over some of these other numbers in practice. So, and then what else do we need? And then last, we need v eta. And what is this? This is minus kx prime to the n over r prime to the n. Okay, so this comes from just examining, how singular, we're a divisor that's, you take a divisor over here that's not contracted by this map. Look how singular it is along E and see where it ends up in here and reverse. Okay, but now we've identified all the things we need here, so we get upper and lower bounds on this one beta invariant. Okay. So this you can obviously put this together if you wanted to. I'm not going to combine these two inequalities to see what it says. Or maybe I'll come back to that, but you combine them and then you get some inequalities on beta of E in terms of these numbers over there. Okay, so how can we apply this? The first application, which I haven't been to, the basic idea is we want to lower and upper bounds on the delta invariant by computing all these for different Sarkisov lengths. So in one direction, if you can compute any of these betas and show that they're negative, then you would be done. It would not be semi-stable, and you would be done. The problem is I haven't been too successful in that when you can't already apply the alpha invariant. So the first thing is if S sub E is already greater than, I don't even know, AE of X, then this would imply that X is not semi-stable. So this is the first, the one that was higher up, the inequality you would use here. Now I computed one of these last night, so just so you can see, it wasn't successful to show that it was unstable. And this is coming from our estimating using, instead of intersection numbers, we're using this log concavity, which is not as precise. So I tried to do this example last night to show something with K unstable. And I'm not saying this could never be used, but so if you take a Del Pezzo, just to see what this is like in practice, of degree 5, dimension 4, like this, you get a Sarkisov length. This is actually how Fujita computed this. He wasn't talking about Sarkisov lengths. In this case, the top map is, as what happens a lot of times, is an isomorphism. And this is 4. Is that a question? Sorry. Maybe yeah. So here I blow up a plane, and the idea is that this is really easy to compute. If you know anything about this map, these bounds are very easy to compute. And so what do we have? We're going to have P4 here. And what did I end up getting? What? I mean, but I was talking about, he computed the beta invariant for this. I'm talking about. Okay. So I'm going to put Fujita. Yeah, so I'm not talking about the. Okay, so the link goes back further. But what did I get for this? And this wasn't successful, but it still shows you how you compute these things. So this is the blow up of a plane that gives you the discrepancy. What else do we need? This is something you can compute pretty explicitly, where this the plane ends up in here, and then what else do we need? Maybe you see what multiple of this. So if you pull back a hyperplane, where it ends up, and that's enough to compute this, along with the volumes of this. And what did I get? I got 2/3 is less than or equal to AE over SE is less than 1.185, which is unfortunate because we know that I don't know what the actual delta invariant estimate is, but I know this is less than 0. And this is coming from my estimate of log concavity. So this Sarkisov link actually does give something that makes this K unstable, but my estimates where I'm just using these 6 numbers are not good enough.
So beta E less than 0, you cannot get it.
Yeah, I'm saying I can't get this. So this is due to, this is what I'm saying about Fuji. But on the other hand, you get some estimate, and it's pretty close, but not good enough. I haven't found one where you can use it and for not proving something's K unstable. I'm going to look for threefolds next where you can explicitly kind of construct these links. Okay, but that's not what I wanted to talk about. But you could do this for that first bound works for K instability, but I'm more interested in the stability side, so that's what I'm going to talk about for the rest. So, and the problem is for the stability side, you can't just worry about one Sarkisov link. First, you have all the different Sarkisov links, and then obviously that's not even enough. There's other divisors, certainly other divisors that you'd have to worry about. But what happens? So if you have a, okay, so this is what we're going to do for, in the other direction. So we want to prove things are K-stable now using Sarkisov links. And what is the main idea? So we have to worry about other E's. Maybe I'm going to say do this note first. So maybe it wasn't clear, but if you estimate things, so if 1 over E, this came up in my pseudo-effective threshold you see over there, also in here. How small can this one, or how big can this 1 over E be? Because this is something, if this was 1, this would be something like the log canonical threshold. Well, E is what multiple we end up with in minus kx. So certainly this is going to be less than or equal to the Fano index of x prime. If you know more about the geometry. So in general, this would be less than the Fano index of x prime, actually where it's effective because we're pushing something effective forward. So maybe say something has to be the whatever the smallest effective multiple of minus kx is. So in particular, for any time that x prime has Fano, if the Fano index of x prime is 1, which occurs in a lot of applications, what are we going to get? Well, we're going to get, this is already going to be log canonical, the most singular divisor. So you look through the estimates and you're going to get that S of E is less than n over m plus 1 times a plus 1. Okay. So this is essentially what I'm going to do for majority of my applications. But if you didn't have something where you're mapping to something of index 1, you could still, you'd have to analyze this more. This number could be larger than 1. And this is enough to prove that these are not destabilizing. So these Sarkisov links. So this implies that beta of E is greater than 0. Okay. So now I have to worry about all my different E's. So let's say you're in a situation where you're only mapping birationally to other things of Fano varieties of Picard number 1. Then all these Sarkisov links are going to be type 2. All the beta invariants are going to be greater than 0. Yeah.
The Fano index of x prime larger than Fano index of x will be negative.
So I haven't been able to prove anything like this. I mean, I've certainly tried to prove things like this, but I haven't. Yeah. I mean, I can't get anything. I haven't been able to conclude anything. This is about as good as I can do. I've tried though. Okay. So the question is, what about other E's? If you're super rigid, you have no Sarkisov links. And we already concluded something there. And that's the idea, is that if you have no other E's and your pseudo-effective threshold is always less than, let's say the alpha invariant of x is less than or equal to 1/2, you can maybe, if you're dealing with canonical thresholds, you can be a little more precise about this. Go look at that more inequality. But let's say the alpha variance greater than 1/2. then what can you say? So I need this assumption if you go back to some of the estimates from before. Well, in this case, then, we're going to break up into two cases. Well, if eta of E is less than or equal to A, well, this corresponds to something, this is like what happens in the birationally superrigid case. And you see that S of E is actually less than or equal to A, which is certainly less than A plus 1. Okay, so there's nothing coming from this that's causing any problems. This is just like in the birationally superrigid case. So this is the case when the neither final, these are all, this is, the discrepancy is, or the, I guess, yeah. So the pair is canonical for all the movable divisors. Okay, so, and in the other case, what do we do if we're in the other case? So if we have some E where this is greater than A, well, the idea is to construct one of these Sarkisov lengths, and this is. The idea is that in this case, you're saying that your Noether-Fano inequalities are not your movable divisor is too singular, and you try to construct a Sarkisov length like this. So y goes to x, goes to y prime as this, and then this could be you'd have to worry about the case where this is a Morey fiber space. But if I say maybe that it's not, in an example, if it's not birational to any other, Morey fiber space with higher dimensional bases, then you already have this type 2 case. So and then you can show that the eta, you can get it, choose an E so the eta would drop if you choose this Sarkisov ring. Right, and what is this basically going to say? Let's see how much time I have. So what can we conclude from this, or what kind of applications? So if we have something birationally rigid now of Fano index 1, this is the type of situation you can use this. I should say this is construct. So maybe that, so here are this type of applications you can get. For instance, if X is birationally rigid, and the alpha invariant is greater or equal to 1/2, then X is K-stable. What other things? So you could explicitly, say you have another birational. If you're only birational to other Fano varieties of index 1, and you need to be careful that when I mean index, I really mean you really have to worry about the smallest effective divisor, not necessarily Cartier, because it can very well happen that the E maps into something that's not Cartier.
When you say only birationals, your Fano varieties mean the only
Sarkis.
spaces have recurrent rank 1?
Yeah. The only other Morey fiber space is maybe, okay. Of Fano index. Yeah, so I'm only interested in the Morey fiber space structures. This would also imply that L plus the alpha invariant is greater than or equal to 1/2. X is K-stable. What else? I guess this kind of question was asked in Hokada's talk. He didn't know how to conclude. Yeah. Do we need that? Yeah. All right. So yeah, X is probably has to be Fano index 1 as well. But terminal and then the alpha invariant. Okay. So and then what else? In another talk, Sichuan asked about separability, and for the same kind of things as right here. What? Terminal. Yeah. So everything works for terminal. You can say some things about KLT things, I should say, as well. You have to change your notion of what a Sarkisov link means, and then we obviously don't know. You know, like if you had canonical singularities, the Noether-Fano inequalities kind of change a little bit. But you can still say something. I don't know how much people are able to prove about things like that as well. But you can certainly use these estimates as well. Okay, so what else? Maybe separability type statements, like in Zitchuan mentioned. For these, and then you have to always assume this Fano index 1. Otherwise, you probably have to compute every other Sarkisov link out. Okay. So these are type statements like if you have a family and you ask for 2 different central fibers and it satisfies assumptions like this, you don't need the alpha invariant assumption for this. Then there can be a unique filling like that. Let's see if do I have any other time. I think I said everything I wanted to say. Yeah, I think I'll end it there. Thank you. What was?
So you were saying that maybe one can say what is the
KLT, yeah. So, I mean, there's something you could still construct similar birational maps. You have to work that. So there's still some you can still compute the pseudo-effective threshold if you have a birational maps like this where everything's KLT and movable threshold. But we don't know how to limit the outputs of that in general.
When is going to be on the high?
Hopefully soon. I will try.
So what's the last statement?
So I don't want to write this. You try to fill in two different families.
Separating this.
Yeah. Oh, sorry. I was thinking. I couldn't think of the word during the talk, and. So the idea is if you have two different families, and you worry about the central fibers having 2 different fillings of the central fibers, and you're something like this. So Zitchuan mentioned we were able to prove something for birationally super rigid things. And he also posed the question for birationally rigid things and birationally solid things. And this, as long as the index is 1 for birationally rigid things, should be fine.
Sorry, what is birationally solid again?
It means...
No vibration. Oh.
Yeah, so this is exactly the type of thing you can analyze with this. So the only thing with birationally solid is you have to worry about every different other every other Fano it's birational too.
This is birationally solid plus index 1.
Yeah, but every other one has to be index 1 as well,
Yeah.
just for the computation to work out. I mean,
Index 1 on all models.
yeah, but you could explicitly compute these numbers if it wasn't index 1. You could compute them in any.
Some other bound mechanism.
Yeah, I mean, and it could very well.
Index, and you can have some other alpha problem.
Yeah, you can, and it's still there's a decent chance. I use pretty rough estimates that it's still.
Yeah.
Not going to cause a problem. Yeah, you should.
So in the final index 2 case, what can you say?
So for hypersurfaces, this was already in Zitchuan a nice paper. We were able. It's essentially it wasn't framed in this framework, but you're going to have a Mori fiber. This isn't going to be a Fano variety. It's going to be a Mori fiber space. There's yeah, you get a bunch of these, and you can explicitly, kind of compute these as well, and then you can get K-stability. So, but that's for a general index 2 hypersurface.
But it's for a big open set.
Yeah.
Not for the whole.
Yeah, not for the whole. Yeah, and the reason is not because this part, the this part is okay. The reason is we don't know all the Sarkisov link structures for the special ones.
But suppose you know.
Yeah, and I think that's fine.
So you have alpha, big.
Yeah, and I think, like, if you knew for other index hypersurfaces all their Sarkisov link structures, this would give you a way to bound, delta invariance of those. Now, that's a hard problem, so, but you only need to know the first Sarkisov link structure out of it, which is maybe a little bit easier than knowing anything birational to it.
We thought about type 1.
Type.
Type 1?
Oh, yeah. I mean, it's not as interesting on the board. I mean, because the applications I gave are all like this, and because the pseudo-effective threshold is the same as the movable threshold for that divisor, so it's not as interesting to write down. So that was more just for time.
So let's understand the